Level 0. Drop a pen right now. It falls without asking permission. It always has, which is such a boring fact that your brain stopped noticing it before your first birthday. The strange part is that there's a place just a few hundred kilometers above your head where that exact same pen wouldn't seem to fall at all. That place exists, and it's not a trick. It's what a body feels like when it's falling around a planet instead of falling onto one. Astronauts aboard the International Space Station aren't floating because gravity switched off up there. At that altitude, Earth's pull is still doing about 90% of its normal job. What's actually happening is that the station, and everyone inside it, is falling continuously around the planet. At the same time, it's moving sideways fast enough to keep missing the ground. It's a 400-kilometer tall building, falling forever and never landing. Then something even stranger happens inside the human body. Your inner ear has no idea how to process this. Tiny crystals sitting on hair cells inside your vestibular system normally get pressed down by gravity, and that pressure is how your brain always knows which way is up. Remove it, and the crystals just drift. Your brain keeps asking a question it built its whole existence around. Which way is down? And for the first time in a person's life, there's no answer. Roughly half of all astronauts get sick in their first 72 hours because of it. But the fluid shift is the part that should genuinely worry you. Blood that gravity normally drags toward your feet instead pools in your face and chest, which is why astronauts look puffy in orbit while their legs, deprived of that daily pull, quietly start to look thinner within days. And underneath the skin, something worse is happening that no one feels at all. Bone density can drop by roughly 1 to 1.5% every month in microgravity because bone only maintains itself under load, and up there, there's no load left to answer to. Up to this point, gravity has mostly been something your body could adapt to. The next setting is where it stops being something you can adjust to at all. Level 1. Sit inside a fighter jet mid-turn and your body suddenly weighs twice what it did a second ago. Your organs do not like that. Blood, now being pulled downward with double the enthusiasm, starts draining out of your upper body and pooling in your legs, and your heart has to fight harder just to push what's left up to your brain, a fight it's already starting to lose. Pilots have a name for the early warning signs. They call it gray out, vision narrowing at the edges, colors fading like a television losing signal. It isn't damaged yet. It's your retina, one of the most oxygen-hungry tissues in the human body, quietly running out of pressure to work with. Most healthy people can tolerate around 2 to 3 G for a sustained period without serious trouble. Uncomfortable, heavy, the face sags a little but still conscious, still tracking, still fine. Still fine at least, until the dial keeps turning. Because gray out has a much darker cousin, and it doesn't announce itself with a warning at all. Level 2. Somewhere around 4 to 6 G held for more than a few seconds, most untrained bodies cross a line they never agreed to. Blood pressure in the brain collapses fast enough that vision goes first, gray, then a tunnel, then nothing. This is called GLOC, gravity-induced loss of consciousness, and it arrives quietly. No pain, no warning shout from the nervous system. You're simply gone, sometimes for 10 to 20 seconds, sometimes with your hand still technically resting on the controls. Fighter pilots train specifically to fight this. Flight suits inflate instantly around the legs and stomach the moment G-forces spike, physically squeezing blood back up toward the brain before it has a chance to pool. Pilots also learn a straining technique, tensing every major muscle and grunting in rhythm to force blood upward using pure muscular pressure alone. With training, tolerance can climb toward 9 G. Without it, most people are unconscious long before that number ever appears on a dial. If trained bodies in pressurized suits are already fighting this hard just to stay conscious, the edge of what the human body can survive has to be somewhere close by. Level 3. 9 times Earth's gravity is roughly where trained fighter pilots, wearing pressurized suits and straining every second, sit at the very edge of what a human body can survive while still functioning enough to fly. Past this point, even elite physiology starts breaking down in new ways. Not just blackouts anymore, but physical injury. Vertebrae can compress, small capillaries inside the eyes can rupture, leaving pilots with a temporary red tint across their vision after extreme maneuvers. In 1954, Air Force Colonel John Stapp rode a rocket sled that decelerated at a peak of roughly 46 G for a fraction of a second, testing the literal limits of survivable deceleration for crash research. He walked away, but with burst blood vessels in both eyes and vision so damaged doctors feared it might be permanent. It recovered, barely. That number sounds almost arbitrary until you realize it wasn't calculated on a whiteboard. It was discovered inside one man's actual body. Every number so far has come from a machine, a suit, a seat, something built by a person. The next jump isn't just larger. It stops being about engineering entirely. Level 4. Jupiter should crush you far more than it actually would. It's 318 times more massive than Earth, so you'd expect its gravity to be off the charts. It isn't, not by nearly as much as its size suggests, because a larger radius also puts you farther from the planet's center, and gravity weakens with distance. The extra mass and the extra distance largely cancel each other out. Stand at Jupiter's cloud tops hypothetically, since there's no solid ground to stand on, and you'd weigh about 2.5 times what you weigh right now. Heavy, exhausting, but nowhere close to lethal on its own. It's almost a letdown after a rocket sled and a human body pushed to its ceiling. A planet 318 times heavier than ours barely outcrushes a person. Mass alone clearly isn't the deciding factor here, and that means something else has to change for gravity to actually start living up to its reputation. Level 5. When a star roughly the size of the Sun finally runs out of fuel, it doesn't explode outward. It collapses inward, crushing almost all of its mass down into an object about the size of Earth. The result is a white dwarf, and standing on one, again hypothetically, since it would kill you instantly through means that have nothing to do with gravity, you'd experience surface gravity somewhere around 100,000 times Earth's. A teaspoon, roughly 5 milliliters of white dwarf material would weigh close to a metric ton. The scale has stopped being about pilots, suits, or muscle entirely. It has become something no biology on Earth has ever had to prepare for, something that only exists in objects that used to be stars. And a white dwarf, believe it or not, is considered the gentle end of stellar collapse. There's a far more violent way for a star to die, and the number waiting on the other side makes 100,000 G look almost ordinary. Level 6. When a star far heavier than the Sun collapses, it doesn't stop at Earth-sized. It keeps crushing down to a sphere roughly 19 kilometers across, while somehow holding on to almost all of its original mass. The result is a neutron star, and its surface gravity is estimated at around 2 billion times Earth's. A piece of it the size of a sugar cube would weigh close to 1 billion tons. Gravity here is strong enough to visibly bend light coming off the star's own surface, curving it around the object so an observer could theoretically see more than half of the neutron star's surface all at once, light literally wrapping around curved space just to reach an eye. Gravity has stopped simply pulling on matter here. It's rewriting the geometry that matter sits inside of. If light itself is already being bent this badly, there's only one place left where it stops arriving at all. Level 7. A black hole is what happens when gravity leaves nothing left to resist it. Cross the event horizon, and the speed required to escape exceeds the speed of light itself, which means nothing, not light, not information, not you, gets back out. At the very center, current physics describes something called a singularity, a point of theoretically infinite density, and by extension, infinite gravitational pull, a place where the equations that work everywhere else in the universe simply stop giving usable answers. This is where science stops handing you a clean number and starts handing you a debate instead. Most physicists suspect a true infinity doesn't actually exist in nature, and that the breakdown is really a sign that general relativity is incomplete at this scale, that some deeper theory, possibly quantum gravity, is needed to describe what's truly happening there. Nobody has that theory yet,